Assalamu alaikum. Today, inshallah, we will solve some problems from the Exergy chapter 8. We will solve questions about closed system, only closed system. We will have another video about also closed system. Then we will upload two videos or three videos about the open system. The first question that we have is question 8025. A mass of 8 kilogram. So we have a mass of 8 kilogram of helium. Helium is an ideal gas. We will benefit from this information later. Undergoes a process from an initial state of 3 meter cube per kilogram. From this unit you can notice the specific volume, V small. That is the initial state, V1 equal 3 meter cubed per kilogram, and T1 is equal to 15 degrees Celsius, and it is in Kelvin, 288 Kelvin. You will add 273 to a final state. The process will go to a final state of V2 equal to 0.5 meter cubed per kilogram and temperature of 80 degrees Celsius. Assuming the surroundings to be at 25 degrees Celsius, that is T naught, we denote the properties of environment or surroundings with naught 0, and pressure P naught 100 kilopascal. He wants from me to determine the increase in the useful work potential, increase of in the useful work potential of the helium during this process. The process is from 1 to 2. There will be an increase in the useful work potential. Okay, what is the useful work potential? Useful work potential is Exergy. How you know it is Exergy? From the definition of Exergy. This summary I will upload it I will put it in the description. The definition of Exergy is maximum useful work that could be obtained from a system at a given state in a specified environment. Already we have state 1 and 2. In specified environment we have the environment T naught, it is given, the surrounding, it is given in the question. Another definition, useful work potential, that is the same sentence that they used in the question. Also again, maximum possible work as it undergoes a reversible process. This represents the useful work potential. So that is Exergy. When he meant useful work potential, he means Exergy. But he said also increase. Increase means from during this process from 1 to 2, from state 1 to 2, means delta. There is a change. So when he says increase in useful work potential, he means delta X. X is the Exergy. Okay, so we need to find the change in Exergy delta X. Okay, is this system is an open or closed? Okay, we know that this video will be about only closed system, but there is no mass flow rate. He said 8 kilogram fixed mass, so we note this fixed mass, no flow. So that is a closed system. Okay, then we have to go to the equation sheet and see what is the equation to find the delta X, the change in Exergy. For Exergy of a fixed mass, non-flow or closed system Exergy, that is the equation x2 minus x1. This will be in kilojoule, and this is equal to m phi 2 minus phi 1. Phi 2 minus phi 1 is the Exergy, but per unit mass. The Exergy change per unit mass is delta phi. So we have the mass, and we will use this equation and multiply it with the mass. We will get the delta x. Okay, so let's write this equation. Delta x in kilojoule is equal x2 minus x1, the exergy of the final state minus the initial state, equal to m phi 2 minus phi 1. Okay, and x2 minus x1 again, equal to m, this m. Then we will substitute this term, phi 2 minus phi 1, with the equation that we saw, u2 minus u1 plus p naught v2 minus v1 minus t naught s2 minus s1. Very long equation, v2 square minus v1 square over 2 plus g z2 minus z1. Did the question mention anything about velocity, kinetic energy, change in kinetic energy? No. So this term will be equal to 0. No velocity. The system is stationary. You will assume it is stationary because nothing is mentioned. Also, there is no elevation from the ground. There is no height. Also, there is no potential energy. This also will be equal to 0. Then you will close the large bracket. You have the mass. It is given in the question. It's 8 kilogram. But you don't have U2, you don't have U1, the specific internal energy, kilojoule per kilogram. You have P naught. It is given here, 100 kilopascal. You don't know. You know V1 and V2. It is given in the question. You know T naught. You don't know S2 minus S1. Right? S2 minus S1. It is not given. So you need to find U2 minus U1 and S2 minus S1. Then you can find the change in the exergy. How can we find this? U2 minus U1. Usually in engineering thermodynamics, we used thermodynamics tables, but we're dealing with steam, water, refrigerant, R134A. But here, that is an ideal gas. For ideal gas, you have to use this equation, CV delta T, T2 minus T1. I put it here in the first page, the questions that you might use in this chapter. So the specific internal energy is equal to CV delta T, T2 minus T1. Okay, but now, okay, I have T2 and I have T1. T2 is 80 degrees Celsius, and in Kelvin it is 353 Kelvin. And also I have T1, but from where shall I get CV? You have to go to table A2. A1, A2, A3 will use it a lot with ideal gas. From A2, you can find here the helium, and that is the specific heat under a constant volume, CV. You will use it with delta U. Here for table A2, you have other gases. For table this, you will not use it. يعني. A3 have other common liquids, solids, and foods. So يعني, before table A4, you will find the tables that you will use for other materials than water or refrigerant R134A. So from table A2, helium, we will take CV, and we will take R, we will use it later, but let's now take CV only and find delta U. CV equals 3.1156, 80 degrees Celsius minus 15. It doesn't matter when you make a difference if it is in Kelvin or Celsius. It doesn't matter. Okay. and the answer will be 202.514 kilojoule per kilogram. Okay, we found U2 minus U1. Then we need to find S2 minus S1. S2 minus S1, when it is ideal gas, you have to use these relations, the entropy change relations for ideal gases under the constant specific heat. Why constant specific heat? That is an assumption that you made when you solve any question. يعني you will choose either constant specific heat or you use variable specific heat. Use this equation or one of these two equations. Depending on what, يعني you make an assumption, you write, I will assume that is a constant specific heat. The specific heat doesn't change for helium, for this ideal gas at the room temperature. And why he made this assumption, why he chose the constant specific heat, he didn't say it is variable specific heat, يعني, if you saw the solution manual, because we don't have the a table A17 for variable specific heat for helium. And we don't have, if you go in the tables, table A17, you will find for air, you will find for nitrogen, hydrogen, carbon dioxide, but you will not find for helium. So he assumed constant specific heat. Then you will use this equation, one of this equation. Which one shall I use? Depending on what you have, we have the specific volume. We have V2 and V1 is given in the question, but we don't have P2 or P1. Yes, we don't. They are not given in the question. So we'll use the first equation to find S2 minus S1 delta S. So let's write this equation: CV ln T2 over T1 plus R ln V2 over V1. CV we use it here 3.1156 ln T2 over T1. Now it is not a difference, then you have to use the Kelvin. Okay, Kelvin T2 353 over T1 288 plus R from the table A2 2.0769. So we'll write 2.0769 ln V2 0.5 over 3. S2 minus S1 will equal negative 3.0873 kilojoule per kilogram Kelvin. Then you already found everything to calculate the delta X, the change in exergy. That is an easy question, but because we are starting, we are just warming up. 8, the delta U is 2.514. I'm substituting in this equation for the exergy change. Plus 100, it is pressure P naught. It is in kilopascal, and keep it in kilopascal because you already calculated U2 minus U1 in kilojoule per kilogram, the entropy change kilojoule per kilogram Kelvin. So you have the kilo. So keep the 100 kilopascal, don't convert it to pascal or anything. V2 minus V1 0.5 minus 3. T naught is 298. S2 minus S1 negative 3.0873. This will give you, inshallah, 6,980 kilojoule. As for the first question, okay, let's see the second question. A piston cylinder device. So we have a piston cylinder device contains 8 kilogram The mass is 8 kilogram. Of refrigerant, now we have refrigerant. The last question, we have an ideal gas. So we are predicting that we will use the refrigerant table. R134A at 0.7 megapascal. So we'll say this is B1, 0.7 megapascal. At temperature 60 degrees Celsius, which is equal in Kelvin 333 Kelvin. Always convert from the beginning because you will often use the Kelvin. The refrigerant is now cooled at constant pressure. When he says constant pressure, means quasi-equilibrium process. يعني the piston is moved down or move up under a constant pressure. Means B1 will remain constant 0.7 megapascal. So we can say B1 equal to B2 because it is constant pressure يعني during the whole process. This constant pressure, we call it quasi equilibrium process. Okay. The refrigerant is now cooled at constant pressure until it exists as a liquid. So that is, if we say that is T1, then T2 is 20 degrees Celsius. If the surroundings are at 100 kilopascal, so B naught is 100 kilopascal. T naught is 20 degrees Celsius. He is asking determine the exergy of the refrigerant. Determine the exergy of the refrigerant. Yes. Determine the exergy of the refrigerant. He wants X at the initial and final sense. He means he wants X1 and X2. And the exergy destroyed during the process, he needs to determine X destroyed. Okay, how can we find X1 and X2? That is also a fixed mass. He said only 8 kilogram. There is no flow. It's a piston cylinder device. It is closed. Then we will use the same equation for the closed system. X1, this equation. We have the mass, then we can say that X equal to M phi. The mass we already have it, but the phi is this equation. Then we say X1 equal to M phi 1 and X2 equal to M phi 2, and we will substitute in this equation. So let's write this equation. X1 equal to M phi 1, M U1 minus U naught plus B naught V1 minus B naught minus T naught S1 minus S naught. The system is stationary. Nothing mentioned about velocity or elevation. There is no kinetic energy, potential energy. So these terms, the V square over 2 and GZ, we will cancel it. So we will the remaining terms are the different in potential, specific potential energy, P naught V minus V naught and T naught S minus S naught. And also X2 will have the same equation, but the subscript will be 2, U2 minus U naught plus P naught V2 minus V naught minus T naught S2 minus S naught. I have the mass. but I don't have U1, U naught, U2. I don't have it. I have B naught. I don't have V1 and V naught. The last question we already given the specific volumes, but here we don't have it. We know that temperature of the surrounding in Kelvin is 293 Kelvin. Okay, and we don't know the change in entropy. So we have a lot of unknowns. How can we found it? Now we have refrigerant, so we will use the tables, the refrigerant table. For the first state, B1, we have B1 equal to 0.7 megapascal, which also equal to 700 kilopascal. Because the tables are in kilopascal, you have to convert, you multiply by 1000. Okay, and what else do we have? We have the temperature, T1 equal to 60 degrees Celsius. So we have to use these two properties to find other properties. We need to find U1, V1, and S1. Also, we need for the second state, we know that it is a constant pressure quasi-equilibrium process. So B1 equal to B2 equal also to 0.7 megapascal equal to 700 kilopascal, and T2 is 20 degrees Celsius. So we can find U2, V2, and S2. For the note that environment properties, we also have B naught and T naught. We use B naught and T naught. B naught is 100 kilopascal, which is equal to 0.1 megapascal, and T naught is 20 degrees Celsius. We want to find also U naught, V naught, S naught. So let's start with the first one. B1 is 0.7 megapascal, 700 kilopascal. Let's go for the table. Thermodynamics table. Refrigerant. We will find it in table A11 until table A13, I think. We have B1, T1, 0.7 megapascal and 60 degrees Celsius. We will go for the pressure table. It is easier. For pressure table, 700 kilopascal is here, and the temperature, my temperature is 60 degrees Celsius, but the saturation temperature is 26.69. So my temperature is higher, means it is a superheated state. Then I have to go to the superheated table. This is a saturated refrigerant table. You have to go to the superheated refrigerant table. So we can say that T set 26.69 degrees Celsius from the table, this one, is less than my first temperature at the first state, which is equal to 60 degrees Celsius. So it is a superheated state. I will go to the superheated table at 0.7 megapascal, at 60 degrees Celsius, and I can get V, U, and S, V1, U, 1, and S1. So U1 will be equal to 274.01, V1 will equal to 0.034875, and S1 will equal 1.0256. U1 is in kilojoule per kilogram, the specific volume in meter cubed per kilogram, and entropy in kilojoule per kilogram Kelvin. For U2, V2, S2, you will have P2, the pressure, and temperature 20 degrees Celsius. As you can see, 20 degrees Celsius is less than the temperature 26.69. Means it is a super subcooled. When the temperature is higher than the saturation temperature, it is superheated. When it is less, then it is subcooled. Subcooled is usually treated as a saturated liquid. So we can say Tsat, this one, the same one, 26.69 degrees Celsius, is bigger than my temperature T2, which is 20 degrees Celsius. Then the state is subcooled, but subcooled is usually treated as a saturated liquid. So we'll get the properties at F, saturated liquid. But saturated liquid at where? At the temperature. At the temperature, you have to go to the temperature table. Yani you can say that the liquid is a function of temperature. You have to use the subcooled when it is approximated to be a saturated liquid. You have to use the saturation temperature table. Saturation temperature table is A11. Okay, A11, the first table in the refrigerant at 20 degrees Celsius, and you will take VF, UF, and SF. The F means saturated liquid, fluid. So U2 will be, I wrote it here, 78.86 kilojoule per kilogram. V2 will be, of course, all of them equal VF, U2 equal to UF, S2 equal to UF, SF. VF equal 0.0008161 meter cubed per kilogram. 0.30063 kilojoule per kilogram Kelvin. That's for entropy. For U naught, V naught, S naught, also you will do the same. What was the temperature of the environment? The temperature of the environment is also 20 degrees Celsius, and the V naught is 100 kilopascal. Okay, yes, here. So I will go to the pressure table, 100 kilopascal. My temperature is bigger, larger than the saturation temperature. It is in negative, so it is superheated. My temperature is larger than the saturation temperature. T naught is larger than Tsat. 20 degrees Celsius is bigger than negative 26.37 degrees Celsius. So it is a superheated state. Superheated. So I have to go to the superheated table. Superheated table. Table A13. 100 kilopascal means 0.1 megapascal at 20 degrees Celsius. That is the line. You will take V naught, U naught, and S naught. So U naught is equal to 248.79 kilojoule per kilogram. V naught will equal 0.23373 meter cubed per kilogram. S naught will equal 1.0918 kilojoule per kilogram Kelvin. Okay, so you found every properties for every state. The rest is substituting. We'll substitute in this equation and this equation, and then we will find the X destroyed So let's first substitute and find x1 and x2. x1 will equal 8, that's the mass, minus the difference between u2 minus u1 minus u0. u1 is 274.01 and u0 is 248.79. Okay. Plus 100, that is P0. P0 is multiplied by the difference between V1 minus V0, 0.03485 minus 0.23373. Minus T0, the difference between the entropies S1 minus S0. The T0 is 20 degrees Celsius, so in Kelvin 293. You have to substitute in Kelvin, not in Celsius. S1 is 1.0256 minus 1.0918. So X1 will be 197.85 kilojoule. And you will do the same with the X2. 8, the mass. U2 is 78.86 minus U0 248.79 plus 100, and also the same pressure P0, 0.000816 is V2 minus V0 0.23373 minus 293, the temperature of the surrounding or the environment, 0.03063, that is S2 minus S0 1.0918, that is X2 will be equal to 308.73 kilojoule. That's for the first part of the question. The second part, they asked for Exergy destroyed. We have two methods or two ways to find the Exergy destroyed. X destroyed can be found by two ways. Either you say T0 times S gene or S generation, or you can find it as it is equal to the irreversibilities. Irreversibility equal to X destroyed, and also equal to this equation. You might say N minus out, or out minus N, the reversible N minus the useful N, or the reversible out minus this equation. You will find it here. The work reversible out minus the work useful out, or the work useful N minus the work reversible N. So which method we will use, and if we use this method, which one shall I use? Is it reversible out or reversible N? Let's see. If I use S gene, I have to first use the entropy balance, Sn minus S out plus S generation equal to delta S system. But I have in this question, the refrigerant is now cooled. Cooled means the piston cylinder and the refrigerant inside it is lost heat to the surrounding. So there is Q out, and I don't have Q out. That is the problem why I cannot use this equation, because when I substitute in this equation, I have to substitute Sn equal Q. I don't have Sn equal to 0. There is S out. It will be Q over T. And I don't have Q, and I don't have the temperature of يعني the temperature of the Q of the يعني of transferring the heat at this temperature, at the temperature of transferring. So I cannot use this equation because I don't have Q. So I have to use the other equation, I equal to X destroyed. We will have another example when we use this equation, and it will be insulated piston cylinder device. يعني هتكون جسم معزول، فمفيش هيت بتدخل ولا بتطلع، فبالتالي هيكون انا بالنسبه لي خلاص كل ده الترم انا هتجاهله. اقدر اقول ان اس جين I will say S gene is equal to delta S system because there is no heat out or heat in. I will have only S gene equal to delta S system. Okay. So what shall I use this for this equation I equal to X destroyed? Shall I use work useful in minus work reversible in, or work reversible out minus work useful out? You have to see the specific volume. Why? Because the piston cylinder can be an expansion process. The piston is now here. That is the piston, and after a while it will be here. So the volume changed. Now the volume is larger. Maybe it will be a compression process. The piston was here, and after the process it became down. So the volume that was V1, and now that is V2. Here that was V1, and now that is V2. So it depends on the process, if it is expansion process or compression process. How can I know? If it is a compression process, then the volume will decrease. If it is an expansion process, then the volume will increase. Compression process is input process. يعني you can say it is input process or input work in if it is a compression process. If it is expansion process, you are producing work to out. So expansion process. Okay, in this question we can see the values of V1 and V2. V1 is 0.0348, but V2 is 0.0030 يعني 3 zeros for V2. So V1 is larger than V2. If V1 is larger than V2, means it is a compression process, because the volume was V1 was a large volume, then it becomes small one, it is V2. So it is a compression process, this expansion process. So I can say it is, if it is a compression process, the V1 is larger than V2. It is a work in. So I will use the equation with the work in, W useful in minus W reversible in. I reversibility equal to X destroyed equal to work UN minus work reversible in. Okay, what is the work UN? Yeah, what is the useful work? What is the reversible work? How can I find them? How can I find them? You have to use the Exergy balance. to find the reversible work, and for the useful work we already have equation for the useful work. For the useful work, the equation is work, the work in the process, or the work in the system, any work in the system, or the actual work in the system, minus the work of the surrounding. The work of the surrounding is already known to us as B naught V2 minus V1. What is the work in this system? Always when we have a piston cylinder, device, the piston is moving. In this case, it is moving down, and it is a compression process. So there is a moving boundary. Yani if I take my control volume as the refrigerant inside, that is my control volume. After a compression, it will be this control volume. This will be my system. The system change the boundary. So when there is a boundary moving boundary, you can say there is a boundary work, WP. So that is the only work in the piston cylinder device that we can see now. So it is the boundary work. What happened? We said at the beginning we have a constant pressure, quasi-equilibrium process. So the pressure is constant, but the change is in volume. Okay, so it was V1, then it become V2. So here this one will be V1 minus V2. So it is similar to the surrounding, but this V1 minus V2, that is we use P naught, but here we use the pressure inside the piston cylinder, B1 equal to B2 اللي هو 0.7 kilo 0.7 megapascal or 700 kilopascal. So the work useful N will equal to P V1 minus V2 minus B naught V2 minus V1. But as you can see, V is the capital V. It is the volume in meter cubed. But we have the specific volume. But fortunately, we have the mass. So we can say that the volume in meter cubed is equal to mass times the specific volume. So this equation, we can write it like this. M B V small 1 minus V small 2 minus M B naught V small 2 minus V small 1. And you have to be familiar with this equation because you will see it a lot. Because in closed system, most of the question we will have piston cylinder, and most of them will contain boundary work with this equation. And sometimes you have to find the useful work, so you will see this a lot of B and a lot of difference in volume and specific volume. This equation, we can take the mass as a common factor and take V1 minus V2 as a common factor, and will be like this: mass B minus P naught. This will be V1 minus V2. And if you distribute this again, you will go back to this if you are not sure. Okay, I have the mass, I have the pressure, I have P naught, I have the specific volumes. I can find work useful N. The remaining is the work reversible N. The work reversible N. Work reversible N, how can I find it? I have to use Exergy Balance. Exergy Balance. Exergy Balance is Xn minus X out minus X destroyed equal to delta X system. When we say reversible work, there is no Exergy destroyed. So always when we say reversible work, this term is cancelled. Okay. Here we said it is a compression process. So work in, not work out. I am doing work in compression process. Then there is no X out. Xn will be my reversible work in, and it will be equal to delta X system that I already calculated in part 1, which is equal to x2 minus x1. This will equal to 308.73 minus 197.85, and it is equal to 110.88 kilojoule. That's the work reversible. If we want to find the X destroyed, the second part, part B, it will be equal to the reversibility and equal to work useful N minus work reversible N. The work useful N was 163.5 minus work reversible N is 110.88, and this will equal 52.62 kilojoule. That is for this question. Let's go for the third question. We'll solve 4 questions in this video, inshallah. أنا تهت خلاص مش عارف فين وصلنا. This question, the radiator of a steam heating system. So we have a steam heating system, has a volume of 20 liter. This is volume 20 liter. If you want to convert it to meter cubed, you have to divide by 1000. Then it will be 0.08 meter cubed, 0.028 meter cubed, and is filled with superheated water vapor. So we know this superheated water vapor. He told me it is superheated, so I will go directly to the superheated table. At 200 kilopascal, that is the pressure. He called it B1, okay. And temperature T1, 200 degrees Celsius. It is steam heating, so you can see it is converting heat to the room, to the air room. At this moment, both the inlet and exit valves to the radiator are closed. From this sentence, you can know it is a closed system. Closed system. No mass flow in or out. Fixed mass. That is why you can say it is a closed system. After a while, it is observed that the temperature of the steam drops to 80 degrees Celsius. So T2 equal to 80 degrees Celsius as a result of heat transferred to room air. So this heat is transferred to room air. This room air, which is at 21 degrees Celsius, so TR or T air room temperature is 21 degrees Celsius. Assuming the surrounding to be at 0 degrees Celsius, so T naught is equal to 0 degrees Celsius. So we have a lot of temperatures. In part 1, he is asking me to determine the amount of heat transferred to the room. He wants to find Q out from the radiator. In the second part, he wants to find the maximum amount of heat. When we read the word maximum amount, we think about exergy, we think about reversible work. So let's see how he wants to find it. The maximum amount of heat that can be supplied to the room, if this heat from the radiator this heat from the radiator is supplied to a heat engine. So this Q, let's put it here, this Q from the radiator out from the radiator can be supplied to the heat from the radiator is supplied to a heat engine. So this Q is supplied to the heat engine, that is driving a heat pump. So this heat engine, the heat engine always take Q hot, QH, which is Q out here, and produce work out, and reject QL to the surrounding. He is saying that a heat engine is driving, so he's driving by the work out from the heat engine, the heat pump. So the heat pump, the work out from the heat engine is the work in for the heat pump. The heat engine is driving the heat pump. Assume the heat engine operates between the radiator and the surrounding. The surrounding, here the surrounding. So it is QL for the surrounding, and he is taking QH. The heat engine is taking the QH from the radiator and driving the heat pump with the work output. He wants to find the maximum amount of heat that can be supplied to the room. Okay, we are taking QH from the radiator to the heat engine, and this QL is for the surrounding. So where is to the room? To the room is from heat pump. Heat pump, from its name, it is pumping heat to the sink, to the heat. For this case, it is for the room air. So it is providing us with Q to the room. Let's say it is Q. This will be Q for heat pump. He wants the maximum amount. The maximum amount that can a heat pump deliver is when it is a reversible heat pump. So that is mean the workout should be a workout from the heat engine is a reversible workout, and is an input reversible work to the heat pump. And this heat pump, of course, it will not take all the work and convert it to Q. It also will reject some Q to the surroundings. Let's say Q naught to the surrounding, differentiated from QL. So he wants to find the Q room. It is the maximum amount of heat that can be supplied. Okay, how can I relate the workout with the Q so I can get the Q? We have the coefficient of performance of heat pump. If it is a reversible heat pump, so it will follow a Carnot cycle, and it is equal to 1 over 1 minus T over T. But which T over T? Usually we say TL over TH. Here TH is the room temperature. I want to heat the room temperature. TL is the rejected heat to the surrounding, which we will call it Q naught, so it is T naught. Also, the coefficient of performance of heat pump, the reversible heat pump, is you can say it is Q room max over the workout from the heat engine. It is a work in for the heat pump. So let's write it also as a work in for the heat pump. Into heat pump, a reversible heat pump. So how can I found the Q max? How can I find the work reversible. For this, it is reversible work. This one is reversible work, yes. And before this, I already want to find QH, which it is Q out that he asked me in the part A. How can I find QA out from the radiator? It is an engineering thermodynamics problem. You will make energy balance around the radiator. So this Q out from the radiator. The energy balance is En minus E out equal to delta E system. I don't have any in work or heat in. I have only one Q out, so it is Q out. There is a negative here in the equation itself. Delta E system consists of delta U, delta KE, delta BE, but I don't have delta KE, so it is 0. I don't have difference in potential energy, it is 0. So delta U, we usually use this one. We have the mass. Actually, we don't have the mass, right? The mass is not given. The mass is not given in the question, so we have to find the mass also. U2 minus U1, and this is equal to negative Q out. And then Q out, if you send the negative in the other side, it will be M U1 minus U2, and you don't have anything of this three terms, M or U or U1 or U2. You don't have anything of them. And also you don't have QH, and you don't have work any, you don't have anything. Okay, let's see how can we solve this question. For here, the reversible work is an out reversible work from the heat engine, right? So let's write the equation also for the reversible work. The reversible work in the last question, we used the Exergy balance. The same here, and usually the reversible work we found it from the Exergy balance. So it is Xn minus X out minus X destroyed equal delta X system. And when we say reversible work, always delta X destroyed is equal to 0. And now reversible work, shall I substitute by Xn or X out? Here it is X out because I am making the Exergy balance on the heat engine. Of course, I should make it on the heat engine because we want to find QR, so we already don't have the other things that before it, QH, work out, reversible. So we have to make Exergy balance about heat engine and found the work out reversible from the heat engine. So Xn is equal to 0 in this case, and for the heat engine it is work reversible because it is coming from the heat engine. So you are seeing who is doing the job. The pump is not doing the job, it is not doing the work, but the heat engine. So we are making about the Exergy balance about the heat engine. That is the reason why heat engine, not the heat pump or not any radiator, not any other thing. So it is a work out from heat engine. So that is why I will substitute X out by work reversible, and already we have negative in the equation. Delta X system, of course, this a capital delta X, so we can say it is M phi 1 minus phi 2. We don't have M. Let's substitute, or let's first distribute this negative. So work reversible will be M. That's phi 2 minus phi 1. Always delta is 2 minus 1. Then when we substitute, it will be phi 1 minus phi 2. Okay. Work reversible also, if we substitute this equation by the long equation, it will be M open a bigger bracket, U1 minus U2 minus T naught S1 minus S2 plus P naught V1 minus V2. I don't know the mass, I don't know anything. I don't know the temperature. Yes, he gave me the temperature. It is 0 degrees Celsius, 273 Kelvin. Don't have the entropy. I have the pressure. Do I have the pressure? I don't have the pressure. Okay, I don't have the pressure. Of course, I don't have the V1 and V2. But you can see from the question, from the figure, there is no change in the volume. That is not a piston cylinder. So V1 is already equal to V2. There is nothing changed. So we can see that V1 is equal to V2. V1 equal to V2. So this term, the last term, will be cancelled. So I don't need to find the B naught or V1 minus V2. So I need only to find mass, the mass. And as you can see, he gave me in the question a volume. So I am predicting that I can use this volume to find the mass. By using volume over the specific volume. And for U1 minus U2, that is a steam, right? Steam, so I have table. I have a table for steam. It is not ideal gas. It is like the refrigerant. I have table for the steam, so I can found U1, U2, S1, S2, find the work reversible, and then we can found also Q out if we found U1 and U2. So let's take the properties that they gave us in the beginning of the question and see. He said that first state or the initial state is superheated, B1 and T1, 200 kilopascal and 200 degrees Celsius. So I will go directly to the superheated table, table A6. Table A6. And he said 200 kilopascal, which is 0.2 megapascal. You divide by 1000. From kilopascal to megapascal, you divide. From megapascal to kilopascal, you multiply by 1000. So it is 0.2 megapascal. 0.2 megapascal. Okay, at a temperature T1 equal to 200 degrees Celsius. So this line. So we can found we don't need for V, it is cancelled. I want to find U and I want to find S. Okay, let's find U and S. I want to take the numbers from this paper. Okay, just take it. يعني no interpolation, no anything. So, but I need also the specific volume because I want to find the mass, so I have also to find the specific volume. Okay, so the specific volume V1 will be equal if we write V1 is equal to 200 kilopascal and T1 is equal to 100 degrees Celsius. This will give me V1 equal to 1.08049 meter cubed per kilogram and U1 2654.6 kilojoule per kilogram U1 and S1 is equal to 7.5081 kilojoule per kilogram Kelvin. This number, yeah. Okay, for the second state, we know that V1 equal to V2, And this is very important information in this question, because when you want to use any thermodynamic table, you have to be given two properties, so you can find other properties. Like here we have P1 and T1, so we can find V1, U1, S1. But for state 2, he only gave me T2 is equal to 80 degrees Celsius, and that is it. He didn't mention any other thing. So knowing that V1 is equal to V2 is very important. So you can say it is, we have T2 and V1 equal to V2, and then you can find other properties. Okay, T2 is 80 degrees Celsius. V2 we already got it here. It's 1.08049 meter cubed per kilogram. Okay, let's see how can I found this. I have the temperature. Of course, I will go to the temperature table A4 at 80 degrees Celsius here. And I have my volume, specific volume, 1.08049. As you can see, it is between 3.4 and 0.01029. Why I am comparing? Because I want to know if it is really a mixture and I have to use this table, or it is a superheated. If it is a superheated, it will be higher than 3.4053. It will be higher than saturated vapor. Okay, but it is between 3.4053 and 0.0010129, so it is a mixture. So I can say it is a mixture because V2 is less than Vg and bigger than Vf, so it is a mixture. Vf is 0.001029 and V2 is 1.08049. Vg is 3.4053. So always when you see a mixture, or you know the state is a mixture, you have to find the quality. Okay, for quality, X2 is equal to V2, the one that you already have, minus Vf over Vh minus Vf. And always Vf is on the right, the one that you have or the one that you want to calculate is on the left, and Vg always down on the left. Okay, that is the famous equation from advanced thermodynamics, and you usually wrote it like this: V2 is equal to Vf plus X VGF. VGF is Vg minus Vf. But if we write it here, it will be okay. You can also put it with any other property, U2 minus UF equal to UG minus UF equal to S2 minus SF over SG minus SF. Let's delete nice. Okay, let's substitute in this equation to find the quality. X2 equal to V2. V2 is 1.08049. That V2 is equal to V1. We get from the last state. Minus Vf 0.010029. It is here, if from the thermodynamics table, this one at 80 degrees Celsius, and Vg is this one. Also, I will get Uf, Ug, Sf, Sg from here. So I can find S2, U2, and I already have V2. Okay, Vg is 3.4053 0.001029. U2 I want to find it, minus UF you will find it 334.97. UG is 2481.6 minus 334.97. Whatever. Okay, S2 minus 1.0756, 7.611. This is the SG and this is F, minus 1.0756. Okay, the values will be x2 equal to 0.3171. You will put x2 with this one or x2 with this one to find s2 and u2, or we can, without calculating x2, you can find you can put this term for v equal to this term for u and find u2 and then use it with s2 any way you like. u2 equal 1015.6 kilojoule per kilogram, and S2 will be equal to 3.1479 kilojoule per kilogram Kelvin. So we have now the properties for S2. So I have all properties that I needed. So let's go back and find some space. To find the mass, we said we will use V over V. The volume given in the question is 0.02 meter cubed, and the specific volume V1 equal to V2 already is 1.08049. So the mass will be 0.01851 kilogram. And for part A, we already got that Q out is equal to M U1 minus U2, right, from here. This one. Okay, so Q out will be the mass 0.01851. U1 is 2654.6 minus U2 was here 1015.6. Then Q out will equal Q out from the radiator 30.3 kilojoule. For the second part B, we want to find the work reversible, and we said that is equal to the mass 0.01851 minus the difference in internal energy, specific internal energy, to U1 minus U2, because it was the work out and we distributed the minus, and like this. 2654.6 minus 1015.6 minus 273, that is T naught, which is 0 Celsius. 7.5081, it is the S1, minus 3.1479 S2. So slow. So the work reversible will be 8.3048 kilojoule. Don't forget to put the bigger bracket, because you do not multiply the mass by the internal energy directly. You have to put the bracket. The mass is distributed in every term in this equation. Okay, then we say that the QH max, the heat supplied from the heat pump, is equal to the work reversible over 1 minus T naught over T room, we usually say TL over TH, but TH was supplied or was pumped to the room air, and T naught is rejected to the surrounding. So we calculate the work reversible is 8.3048. 1 minus T naught is 273 over 294 will give us 116.27 kilojoule. That is QH max. That is for this question. We have the last question, inshallah, 833, and good luck for me to find it.